Okay, picture this. Imagine our modern world, but suddenly you strip away every single electric light, every train, every computer, and, yep, even your smartphone. We'd be plunged right back into the dark ages in an instant, wouldn't we? Well, today in this explainer, we are diving deep into Chapter 6, Electromagnetic Induction. We're going to look at the exact scientific spark that, literally, prevents us from living in the dark. So, there's this fantastic story about the legendary experimental physicist Michael Faraday. When he first made his major discovery public back in the 1830s, someone actually asked him what practical use it had. His response, "What is the use of a newborn baby?" I mean, it sounded like completely useless, head-in-the-clouds theoretical physics at the time. But as you'll see, that seemingly helpless newborn baby grew up to birth our entire modern electrical civilization. It's crazy to think about.
And we actually have two proud parents of that discovery, Michael Faraday over in England and Joseph Henry in the USA. Right around 1830, completely independently of each other, which is wild, these two pioneers conducted these long series of experiments, and they conclusively proved that if you create relative motion between a magnet and a wire loop, you produce an electric current. Boom, a monumental breakthrough in human history. Here is our quick roadmap for today. We'll start with a newborn baby, move right into understanding magnetic flux, cover Faraday and Lenz's laws, explore motional EMF and inductance, and finally arrive at the AC generator.
All right, let's just kick things right off with Section 1, a newborn baby, the dawn of induction. So before the 19th century, scientists basically thought electricity and magnetism were completely unrelated things, totally separate. But then you had experiments by physicists like Oersted and Ampere, and they proved that moving electric charges actually produce magnetic fields. This was a huge deal, and it begged a massive question. If moving charges produce magnetic fields, well, can moving magnets produce electric currents? Does nature permit a two-way street? Faraday and Henry asked this exact question, and spoiler alert, their experimental answer was a massive, resounding yes. Now, to really grasp how they prove this, we need the right vocabulary. Moving on to Section 2, magnetic flux, understanding the concept. Okay, so technically, magnetic flux is defined as the product of a uniform magnetic field and the surface area perpendicular to it, and it's measured in this scalar unit called Webers. But honestly, a much better way to visualize it is like rain falling through a hula hoop. Just imagine it. The magnetic field is the rain, right? And the area is the hula hoop itself. So the magnetic flux is simply the total amount of that magnetic rain passing through that specific area. Easy enough, right?
With the concept of flux firmly planted in our minds, let's jump straight into Section 3, Faraday and Lenz's laws, the math behind induction.
All right, here's the heavy hitter. Faraday's law of electromagnetic induction. It essentially states that the magnitude of the induced EMF, and hey, you can just think of EMF as voltage for now, is equal to the time rate of change of magnetic flux through a circuit. The absolutely crucial phrase there is time rate of change. Listen, you cannot get electricity just by holding a magnet perfectly still inside a coil of wire. It just won't work. The magnet has to be moving. That magnetic flux must be actively changing over time. No change, no current. It's that simple.
But look, we all know nature doesn't just hand out free energy. If an induced current didn't actually oppose the motion creating it, we'd be living in an impossible reality. We'd have perpetual motion machines generating infinite energy without expending any mechanical work at all, which would be cool, but it's impossible. Instead, actual reality is governed by Lenz's law, deduced by the German physicist Heinrich Lenz. His law basically says that the induced current always flows in a direction that opposes the change in magnetic flux. Because of this repulsive force, you actually have to do physical work to push a magnet toward a coil. You're fighting against it. And that mechanical work is exactly what gets converted into electrical energy, plus some joule heating. It is just a perfectly elegant demonstration of the conservation of energy in action.
Now that we've got moving magnets down, let's flip the script. Section 4, motional EMF and self-inductance.
So what if we move the conductor instead? That is motional EMF, generating induced voltage by moving a conductor through a magnetic field. Picture sliding a metal rod across a U-shaped rail that's sitting inside a uniform magnetic field. Because that rod is physically moving, the free charges inside it actually experience a Lorentz force. That's a magnetic force that physically pushes the charges right along the rod, generating an electric current. So you can produce an EMF simply by moving a conductor, effectively changing the area of your circuit, and therefore, you guessed it, changing the flux.
And when it comes to the coils themselves, we run into something called self-inductance. We represent it with the letter L. This is basically a coil's natural built-in opposition to changes in its own current. Think of it as electrical inertia.
You know how mass and mechanical physics resist any change in physical motion? Like how it's hard to push a really heavy boulder? Well, inductance works the exact same way, but it opposes the growth or decay of current in an electrical circuit. It likes things to stay right where they are.
All of this incredible 19th century physics leads us perfectly to our final section, Section 5, the AC generator, powering our world.
Remember Faraday's so-called useless newborn baby? Well, it grew up into the AC generator. Heavily credited to the brilliant inventor Nikola Tesla, this is a highly evolved machine that basically converts mechanical energy into electrical energy. Seriously, every single time you flip a light switch, you are tapping directly into the power of this exact technological application. It's the engine of the modern world.
So let's quickly walk step by step through exactly how this marvel works. Step 1. An external mechanical force. Think of water rushing through a massive dam or hot steam spinning a turbine physically rotates a coil of wire, which we call an armature, inside a uniform magnetic field. Step 2. As that coil spins around, the angle between the magnetic field and the face of the coil is constantly changing, which leads to step 3. Because that angle is changing, the magnetic flux passing through the coil continuously varies over time. And finally, step 4, just exactly as Faraday's law dictates, this constant time rate of change in flux induces an EMF, generating an alternating current. The polarity of the voltage literally flips back and forth as the coil rotates in circles. It's a real game changer.
It is just truly astounding to think about. The discovery of electromagnetic induction literally took humanity from a world lit by oil lamps and candles to a world powered by massive, continent-spanning electrical grids. So I want to leave you with this final, kind of provocative thought as we wrap up today's explainer. If a seemingly useless newborn baby in a drafty physics lab in the 1830s completely transformed our entire modern world, well, what seemingly useless newborn baby in theoretical science today is just waiting to power our tomorrow?